Heat engines and energy efficiency recap internal energy and the first law. Before we talk about heat engines, let's quickly remind ourselves of what we already know. Internal energy is the total kinetic and potential energy of the particles in a system. From the first law of thermodynamics, we learned that the change in internal energy equals the heat added to the system plus the work done on the system. Heat is positive when energy is added to the system. Work is positive when work is done on the system. If a system expands and does work on its surroundings, the work term is negative. These ideas are essential for understanding how heat engines operate. Adiabatic processes and internal energy. Let's think about a special situation called an adiabatic process. Have a go at answering these questions. Once you believe you have answered them, press play and we will continue together. In an adiabatic process, no heat enters or leaves the system. If a gas is compressed rapidly in an insulated cylinder, no heat has time to escape, so Q equals 0. Work is done on the gas, which increases its internal energy. Because internal energy increases, the average kinetic energy of the particles increases, and that means the temperature rises. This is why a bike pump warms up when you pump air into a tire quickly. What is a heat engine? Now let's define a heat engine. A heat engine is a device that converts thermal energy into useful mechanical work. It does this by taking in heat from a high-temperature source, converting some of that energy into work, and releasing the remaining energy as waste heat to a cooler environment. Common examples include car engines, steam turbines in power stations, and jet engines. How heat engines work. All heat engines operate in a cycle. First, heat input occurs when fuel is burned or heat is supplied, raising the temperature of a working substance, usually a gas. Next, the hot gas expands, pushing a piston or turning a turbine. This is where useful mechanical work is done. Then, heat output occurs as the cooler gas releases waste heat to the environment through exhaust gases or cooling systems. Finally, the system returns to its initial state, ready to repeat the cycle again. Internal versus external combustion engines. There are two main types of heat engines. Internal combustion engines burn fuel inside the engine itself, usually inside cylinders. Petrol and diesel car engines are examples. They are relatively efficient but produce emissions directly. External combustion engines generate heat outside the engine and transfer it to a working fluid. Steam engines are an example. They are generally less efficient but can use many heat sources such as coal, solar energy, or nuclear power. Energy flow in a heat engine. In every heat engine, energy flows in a specific way. Some of the input energy becomes useful work. The rest leaves the system as waste heat. No matter how well designed an engine is, not all the input energy can be converted into work. Energy efficiency. Explained, this brings us to the idea of efficiency. Efficiency tells us how well a device converts input energy into useful output energy. Efficiency is calculated using useful energy output divided by total energy input, multiplied by 100%. For example, if a car engine takes in 1,000 joules of energy from fuel and produces 250 joules of useful motion, the efficiency is 25%. This means 75% of the energy is lost, mostly as heat. Fill in the blanks example. Let's apply this idea. Have a go at filling in the blanks of this sentence from the words below. Once you have done this, press play, and we will continue this together. A coal-fired power station takes in 5,000 megajoules of energy and produces 1,800 megajoules of electrical energy. The efficiency is 36%. The waste heat released is 3,200 megajoules. This shows how much energy is lost, even in large-scale systems. Sources of energy loss. Why is efficiency always limited? There are several unavoidable sources of energy loss. Friction between moving parts converts energy into heat and sound. Heat dissipation occurs as hot engines lose energy to the surrounding air. Exhaust gases carry away thermal energy. Incomplete combustion means not all fuel energy is released. All of these reduce useful output. Real-world efficiency. In real systems, efficiencies are often quite low. Petrol car engines are typically only 20 to 25% efficient. Power stations operating on coal or gas are around 30 to 40% efficient. Nuclear power stations are also around 1/3 efficient, with large amounts of heat lost to cooling systems. Improving efficiency even slightly can save enormous amounts of fuel and money. Heat engine efficiency. Check. Let's check our understanding. Pause the video here and have a go at answering these questions. Once you are finished, press play and we check them together. A heat engine produces mechanical work by absorbing heat from a hot source, converting part of it into work and releasing the rest to a cooler environment. If a power plant takes in 800 megajoules of energy and is 30% efficient, the useful output is 240 megajoules. No heat engine can ever be 100% efficient because the second law of thermodynamics requires that some heat must always be rejected to a colder reservoir. Environmental and economic impacts. Efficiency has real-world consequences. Low efficiency means more fuel burned, higher costs, and greater pollution. Waste heat and exhaust gases contribute to air pollution and climate change. Engineers must balance efficiency with cost, size, safety, and emissions. Improving efficiency is one of the most important steps toward sustainable energy systems. Final summary. Let's summarize the key ideas. Heat engines convert thermal energy into mechanical work. Because energy is always lost as waste heat, no engine can be 100% efficient. Efficiency is calculated as useful output divided by total input, multiplied by 100%. Real-world engines, from cars to power stations, lose large amounts of energy, which has environmental and economic impacts. Improving efficiency is critical for a sustainable future.